So my name is Arun Satno, and I'm a data scientist at the Pacific Northwest National Laboratory. So I'm joining this conference from the West Coast in US, where it's slightly past midnight. And this work is in collaboration with Arif, Milan, and Ashutosh, who are my colleagues at PNNL here. And so what we have today is basically development of a virtual test bed and some initial results on applying AI algorithms to boost operational efficiency in road transportation networks. So the outline is basically, I'll start with quick motivation and talk about some prior work, then talk about our approach and contributions. Then we'll talk about the virtual testbed development with SUMO and look at the test case. And then I'll present some results from our work. And we're kind of trying to also interpret the decisions taken by the AI algorithm, but that part of the work is still in its early stages. So I'll do my best to give you an explanation of why the AI is doing something when we look at the results. And then we outline with our ongoing work and conclude at that point. Motivation, basically, like there's hardly any motivation needed for this work because it's a global issue with increasing traffic congestion and specifically.
Sorry, you have to move to the next slide because we can only see the first slide.
Okay, so
you can use the arrow. Yes, thanks.
Yes, okay. So I think there is some issue with the presentation mode. So I'll just kind of keep it at this. So that way you can see the slides. Can you still see the second slide now?
We can see the second slide already, but as I said,
okay.
You can just press the button, the green button on the left side. It is above the home icon in your document. There's a home icon on the left side, and then above the home icon, there's a green button. You can press it. The green circle, the small green circle on the left side.
So I'm on a Mac, so it looks a bit different. So if this is working, then I'm going to.
Yeah, it's okay. Yeah, continue.
Yeah, okay. Yeah. So obviously, like reducing traffic congestion is a problem that's faced all over the world, and there is a clear need for tackling this problem, especially when there are collisions and incidents, which, if left unmitigated, they can cause cascading failures affecting large parts of the road network. And the nice thing about the recent developments is there's a lot of Internet of Things infrastructure and communications infrastructure in the form of 5G, etc. That's helping us sense and get a lot of data about the traffic conditions. And as a result, whenever there is a lot of data, there's scope for AI algorithms to come into picture and help optimize the problem at hand. So the research in the context of AI algorithms and reducing traffic congestion is typically the focus has been more on the control of traffic lights, specifically the phases, timing, and the coordination. But there is a clear gap in the research related to traffic management, specifically when you have collisions and crashes. What kind of detouring strategies, optimal strategies can be employed to reduce congestion and improve the travel times. So in terms of prior work, I have there's a wide body of work related to application of deep reinforcement learning algorithms when it comes to road transportation networks. I just have outlined a few of them. The first reference basically is a survey paper, and it gives flavor for a lot of different types of applications for deep reinforcement learning. So I'm using AI and deep reinforcement learning interchangeably. So those are the main algorithms that are kind of employed in these control algorithms. And then in terms of going into the little bit of specifics on the different types of applications, obviously adaptive traffic signal control is a very important application that many papers talk about. And here is one example towards 1000 light, where they apply decentralized deep reinforcement learning algorithms for large scale traffic signal control. And then you have route optimization, where basically multi-agent reinforcement learning is employed for ramp metering. And this is basically to control the flow before it enters the network, the freeway network, so that you're kind of trying to optimize the incoming traffic itself. On the other side is basically traffic management. There you kind of come up with interventions to ease congestion after the traffic demand has taken place, and there are external factors such as collisions and crashes, and that's essentially our work. So in terms of contributions, we basically develop a virtual test bed by using the SUMO traffic simulator with the TrackEye controller and the OpenStreetMap based networks. And then we interface that with some of our own Python code and the Ray deep reinforcement learning library. And put together, we kind of come up with this virtual test bed. And what we do is also take real world data on traffic profiles, and we kind of develop a calibrated model. With that, we are able to generate with some randomization different traffic profiles which can be used for training and testing our model. And we also come up with a kind of a novel optimization based problem formulation based on the macroscopic fundamental diagram. This is a fairly simple formulation, and the details are actually in the paper that we are working on, but I'll give a quick flavor for what this looks like. And then we apply deep Q network and the Advantage Actor Critic methods, basically to a value-based method and a policy gradient-based algorithm to provide detouring actions to improve the congestion with and without accidents. And finally, we demonstrate a simple transfer reinforcement learning example, wherein we train on just a regular congestion and we deploy it on the accident scenario, just to kind of show that in a real world setting where not a lot of data is available about accidents, we can actually just train on the congestion scenarios and deploy it for the accident scenarios. So here is the architecture basic that we have developed. Essentially, we have the deep RL controller in the center, and we have the SUMO simulator over here, which is kind of talking to the TrackEye controller, which is sensing and actuating the decisions taken by the RL controller. And then this also kind of takes input from the network topology and the calibrated traffic profiles. And we write out a lot of data from the TrackEye sensing module, and that's essentially used for model training eventually. And we're working on the explanations and visualizations. So I don't have much on that yet, but that's something that we're working on. So a quick description of the test case. So our focus is on our 2.5 miles section of the Interstate 5 freeway in the city of Shoreline, Washington, pretty close to Seattle on the West Coast. And this is basically a 4-lane freeway, and it's very heavily utilized. And the particular section that we are talking about basically has a lot of issues in terms of frequent incidents and crashes, leading to large backups. So I kind of picked that as the test case. So here I'm showing the Google Maps kind of screenshot and also a schematic which shows the model that we are actually looking at, which is you have the traffic entry from the on-ramps, and then you basically have 5 different detectors that we have placed, virtual detectors, which helps us sense the data. And there are 2 different exits, and there is an arterial that accompanies this freeway. And you kind of see the network, different routes that are possible with this network. So you can pass through the freeway and then, or you can take exit 1 and rejoin the freeway, or you can take exit 2 and rejoin the freeway, which is what we use in when we do the detouring. And the red star, this part is basically where the accident happens between exit and exit 2. These are all simulated within SUMO. So how we set up the deep reinforcement learning based controller, we basically have a total of 22 detectors. So there are 5 that I showed you, and there's 1 per lane. So there is total of 20 over there, and also 1 detector on each of the 2 exits, giving us 22 detectors. And then we actually look at counts and average speeds at each of these 22 detectors over 1 single RL time step, which is about 10 minutes. And this defines the 44 element state vector. And then the action space is defined by a 16 element vector. So this is denoted by F1 and F2. And these are the percentage of time for which the vehicles on the rightmost lane will take the exit. And F1 refers to exit 1 and F2 relates to exit 2. You could randomly exit the vehicles, but it kind of makes sense when you use dynamic messaging signs to actually use a duty cycle based control, because that's the most practical in the current setting. But if you had CAVs, for example, which are connected automated vehicles, then you could probably use a randomized strategy. But here we stick with the duty cycle based control. So there are 4 possible values for F1 and F2. And then that defines the 16 element vector for the entire act space. And the reward function design is actually a bit harder than what it looks like. And it took us some exploration, but we did end up with 2 different types of rewards, which is a count-based reward, which is based on a flow formulation. You want to maximize the total number of vehicles that are transported across the freeway from an operator perspective. So that's one type of reward. But as I explained later, we also look at a surrogate reward in the form of average speed. So you want to maximize the average speed. And the first reward is basically more towards a system level objective, and the second is more towards an individual type of objective. So I'll probably skip this or go over this slide very quickly. So this is something that we are trying to formulate in terms of the macroscopic fundamental diagram. So this is a typical MFD for a freeway, and we kind of hypothesize that P1 is the initial operating point, and you want to move towards the system optimal, which is P star. So you try to detour the vehicles accordingly. But then, since you are detouring these vehicles through the arterial itself can get congested, and that can backflow towards the freeway. So this is an optimization problem with the arterial and the freeway network put together. So we hypothesize that instead of going all the way to P star, you probably end up at P2, and the slack, the difference between P2 and P1 is taken up by the, in terms of density, is taken by the arterial network. Again, this is a cartoon, and these are not absolute values. And over here, you can see how that translates to speed versus density. And over here on the right side, I'm showing the SUMO simulations for deriving the fundamental diagram, and it looks like it came out pretty well in terms of the comparison with the ones in the literature. So that's kind of a mini validation that we did. So in terms of main results, I'll very quickly go over the results because we just have a few minutes. So the main thing is the count-based reward did not lead to stable training. There is a lot of instability in the training, as you can see from the figure on the top. So it turns out that using the surrogate, which is a speed-based reward, turned out to be more stable. So we kind of ended up using that for our optimization. And what I'm showing in the center figure is using the speed-based reward for optimization. But while that happens, we also plot the count-based reward. And as it turns out, initially both the speed and the count they increase. But then after a while, because of the shift in the operating point, while we get an increased speed, that comes at the cost of exiting more vehicles, which means the count on the freeway actually drops. And again, over here in the bottom, we show the results for the case with the accident, wherein the speed increases up to a point.
1 minute.
Yeah, so I'll try to wrap it up. And then it kind of tapers off. So there is only so much you can gain because of the arterial bottleneck. So that's why you see the leveling off. And when you deploy these controllers in a test setting, not the training, but actual deployment, you can see the increase in the average speeds. And we can see that the A2C algorithm, the Advantage Actor Critic, performs much better than the DQN algorithm. And finally, here we have some results from transfer learning, wherein you kind of train the model on just a regular congestion, but then you deploy it on the accident scenario. And again, here we show that if you don't do anything, this is the speed achieved, the average speed. And then the A2C controller, when trained with the accident, is this orange profile. But if you just train it on the regular congestion, it kind of comes pretty close to the one where it was trained with the accident. So in case of sparse data where you don't have a lot of accident data in the real world, you could actually use transfer learning, which is what we are able to demonstrate here. So in terms of conclusions and future work, so we have come up with this prototype and we'll be open sourcing this testbed probably sometime in the next 3 to 4 months. And we showed some initial results wherein AI algorithms was able to kind of use detouring with some route optimization to improve the speeds and the flow on the freeway networks. And finally, we also illustrated the efficacy of a simple transfer reinforcement learning strategy. And the current work is basically focused on scaling the network size and employing multi-agent DRL models. Because if you have multiple decision-making points, then there is dimensionality explosion. So you may not want to do a single agent, so you might want to do multi-agents, which is what we are working on. So thank you very much for your time today, and apologies on some of the Zoom related issues. So if we have time for a question or two, I'm willing to take that. If not, we can kind of do it over email.